Okay, good evening, everybody. I hope you all enjoy your long weekend. Oh, 50? Is it crooked? This here? This is better? Oh, okay. Okay, thank you. Okay, I hope you all enjoy your long weekend. We do have a lot of material to cover today. But before we start the session, I want to make a few announcements. As you know, the second class exam is scheduled for next week, Thursday, October 18th. And so because of that, what we are going to do next week, there will be 2 online review sessions next week. And also tomorrow, that is Wednesday, the October 10th, tomorrow. The online review session for tomorrow will be based on the one of the previous second exam, questions from one of the previous second exams. And then the online session for Monday at 8 p.m., that is Monday, October 15th, that will be based on our chapter 8, end of chapter questions. And because of that, I have assigned the end of chapter question in chapter 8 of ours for your own work assignment, and that is due next Wednesday. Due next Wednesday at 11 p.m. Not this coming now. Wednesday, October 15th. It's due Wednesday, October 15th. Oh, I'm sorry. Wednesday, October 17th. Yes. Yes. And then the online review session that we are going to have on October 15th, Monday, that will be based on our end of chapter question. And then the online review session that we will have on Wednesday, October 17th, we are going to continue to review for the second exam. Okay? So make sure you just a minute. Make sure you put all of those in your calendar. So 3 review sessions, 1 tomorrow, October 10th at 8 p.m. I will send you the link. And then another one on Monday, October 15th. Then another one on Wednesday, October 17th. Yes, go ahead. Yeah, I did already. Yeah, I have the previous exam in Blackboard already. So when you come for the review session tomorrow, please make a copy of it so we could go over the questions together. Yes. Yeah, for the exam, good question. For the exam on October 18th, we are only going to be working with chapters 5, 7, and 8. 5, 7, and 8. And also, if you notice, there are some aspects of chapter 6 that we have covered already. So, but essentially, it will be chapters 5, 7, and 8. Okay? Okay, now, so let us start with today's session. If you recall, when we left on Thursday, we started with chapter 7, which was concerned with the chemistry of alkenes. And before we left, we started the electrophilic addition reactions to the carbon-carbon double bond. So what I want to do is simply just go over a few of the items that we went through last Thursday before we go to chapter 8. Okay, if you take a look at the slide in front of you, here we want to discuss electrophilic addition reaction of alkenes. Taking a look at this slide here, you have this molecule here, in which you have a carbon-carbon double bond. One of the carbon-carbon double bond is attached to a methyl group, and the other carbon is attached to an hydrogen atom. Now, for the electrophilic addition reaction to alkenes, our concern is the addition to the carbon-carbon double bond. The rest of the molecule has nothing to do with this reaction. For example, you take a look at this here. What are we doing here? We are adding this hydrogen to this carbon here, and that is what we get here. And then in the course of adding this hydrogen to this carbon, we form a tertiary carbocation. And before we left on Thursday, we also told you that the formation of the tertiary carbocation generally proceeds to the formation of the most stable carbocation. In other words, if you have a choice of forming two types of carbocation, the hydrogen will add to that carbon that is attached to more hydrogen. Okay? In this case, this hydrogen here is added to this carbon here. Notice that this carbon has no hydrogen attached to it. Okay? So therefore, we expect this hydrogen to attach to this, and then we form the intermediate carbocation. And of course, this intermediate carbocation is a tertiary carbocation. And from there, you now have the bromide anion that is formed will now act as a nucleophile to form the final product, which will be this here. Okay, so the net process of this reaction is the addition of the hydrogen and bromine across the carbon-carbon double bond. Okay, so we call this electrophilic addition reaction, because in this case, the carbon-carbon double bond, the pi electron in the carbon-carbon double bond is acting as a nucleophile. Acting as a nucleophile, whereas the hydrogen, the proton in this molecule here is acting as an electrophile. Okay, and here the bromide that is formed now acting as a nucleophile attacking the carbon of the carbocation, positively charged carbon. Okay, what we just described for you, this is just this slide here simply gives you the overview of what I just described for you, in which you have the pi electron of the carbon-carbon double bond attacks this proton here. The hydrogen-bromine bond will break heterolytically. This is an heterolytic cleavage, in which case the bromine is attracting all of the pair of non-bond, the pair of covalent electrons to itself to form the bromide anion, which is what you have here. And then the final product is this one here. Okay, this type of reaction, we also informed you that this is what we call a Markovnikov addition reaction. And we told you that in the Markovnikov addition reaction, the proton or the electrophile is added to the carbon of the carbon-carbon double bond that has more hydrogen. Okay. Okay, this is just another example of the same reaction. Here you have hydrogen bromide adding across the carbon-carbon double bond right here. In this particular instance, it does not really matter where the hydrogen goes, because you have here a symmetric carbon-carbon double bond. So The hydrogen could go to any one of these carbons here. Now, if you take a look at this next slide, see what we have here. What is happening here? We have this molecule here, carbon-carbon double bond. This carbon is attached to 2 hydrogen atoms, whereas this carbon here is attached to no hydrogen at all, right? So if we do electrophilic addition reaction, we will expect the hydrogen to come to here. And that is what we have here. If you look at this reaction here, this is the product right here, starting with the intermediate carbocation, and then the final product. This product here, this is not formed. This is not formed. Okay, and that goes to show the fact that in any electrophilic addition reaction, the reaction will proceed via the more stable carbocation. And that is the basis of the Markovnikov reaction. In other words, in any electrophilic addition reaction, the proton or the electrophile will add to that carbon such that you form the more stable carbocation. Okay, and that is the basis for the Markovnikov reaction. Okay, also, before we left, we also told you the order of stability for carbocations. We told you that the tertiary carbocation is more stable than the secondary carbocation, and the secondary carbocation is more stable than the primary. And of course, the least stable of all the carbocation is the methyl carbocation. And this will guide all of the reactions that involve the formation of carbocation. So because the carbocation is a very, very important intermediate in organic synthesis. Okay, so we are going to be seeing a lot of these intermediates as we go along. Now, let us now begin to do some problems. Supposing I give you this molecule here, and I have this. What will be the product of this reaction? Keep in mind, at this point, I am not asking you for the reaction mechanism. But for you to know the product, you need to have some idea what the reaction mechanism is. So what will be the product of this reaction? Where will the hydrogen go? Let me use a different color here. Okay, let's call this carbon 1 and carbon 2. Where will it go? Carbon 1. Okay, so you expect the product to be this? Okay. So we expect the hydrogen is here, and then of course the bromine goes, or the chlorine goes right here. Is that correct? Okay, now. How do you what? How do you know? We just told you. That is,
how do you get to that? Like what steps are you taking for you to know that
No, are you asking me for the reaction mechanism? Okay, now. Okay, we know that we know that this hydrogen goes to this carbon here because it contains more hydrogen, right? And then in the process you form a carbocation, and that carbocation is not attacked by the chloride to form this here. Now, so this is one way I could do this. I could very well do this. Okay? I would say, give me the reagent for this transformation, right? That is one way I could ask you that question. Or I could do this. I say this compound A somewhere here. Compound A reacts with hydrochloric acid to form this compound here, B, and then I ask you to give me what is the structure of compound A. So those are the kind of ways in which we could ask you that question. Okay? Or I could do this. So in other words, this particular question here, this equation right there are three possible questions I could ask based on that equation. I could also do this. I could do that, and I say, give me the product of this reaction. So you can see, based on that equation, I could ask you three different questions, and all pointing to the same understanding of the concept. Okay. So, for example, what if I give you this? What will be the product of that reaction? Keep in mind, our focus is only on the carbon-carbon double bond. If the molecule could be as big as whatever you want to be, it doesn't really matter. The focus is on the carbon-carbon double bond. Okay, so don't let the molecule intimidate you because you have a big molecule and say, oh, this is something going on here. It's no different from what we've been doing. So what will be the answer? The bromine goes to top, and why? Because it has less hydrogen, but what is the fundamental reason for that? Because it goes through the intermediate carbocation that is more stable, right? That is the fundamental, that is the fundamental reason. Even though that is the reason why mechanical reaction or mechanical rule, that is the reason why it works. Okay? So in this case, we form this product. Say that again. Oh, I thought you were telling me. Okay. So therefore, the product is this here. Okay. Okay, so let us go back to okay, we've done all of that. Okay, in this case, here, see what happens here? The hydrogen goes here. Of course, the bromine goes here. Because this hydrogen here, or this carbon here, is attached to one hydrogen, and this carbon here has no hydrogen attached to it. And that is why you get this product. Now, we could also add water across the carbon-carbon double bond. Yes.
Can you go back to the question of the two, connected together? Can you go back to that?
Okay, just a minute. Okay, let me make this point. We could also have a case in which we add water across the carbon-carbon double bond. Okay, we will give you the mechanism for that later. We could add water across the carbon-carbon double bond. The net process is the addition of the element of water, which is hydrogen and hydroxide. And that is what we see here. And you see, this is also still follows the Markovnikov rule. That addition also follows Markovnikov rule. This is the reagent we use for that. Notice what are we doing here? See where the hydroxy is? This carbon here is where the hydroxide goes, which is what this is right here. And of course, this carbon here is this carbon. You notice that is where the hydrogen goes. So you could also have addition of water across the carbon-carbon double bond, just as we have the addition of hydrogen and bromine or hydrogen and chloride. Yes. Yes, yes, yes. Okay, so now you want me to go back to the last one. Okay. Okay. Why didn't I do what?
You didn't add the ethane, you just made it miss. I mean,
Oh, I'm sorry.
Okay.
No, that was my error. Okay. Okay, now, on this slide, I do not want you to spend too much energy on this. One of the reasons, remember we told you earlier that the carbocations are the most substituted carbocation. In other words, the tertiary carbocation is more stable than the primary or secondary or methyl. The reason for that, there are two basic reasons. We have either inductive effect, in other words, why do we have, whenever we have alkyl group attached to carbocation, the carbon of the carbocation, which is positively charged, why is it that when you have the alkyl group, it is more stable? So there are two explanations that we could give. Either we could give explanation in terms of inductive effect or what we call alpha conjugation. If you take a look at this here, you have this carbocation here. Of course, the carbocation has an empty p orbital. This is what you see here, an empty p orbital. And then you have this carbon here attached to hydrogen. As we know, based on electronegativity of carbon and hydrogen, carbon is more electronegative than hydrogen. So it is therefore pulling electron to itself. So in essence, what we have here is that this carbon here is a lot richer in electron because the net effect of the electronegativity difference is that you have this carbon here has a partial negative charge, while this side of the molecule has a partial positive charge. And that, in effect, helps the positive carbocation to pump electron into that carbocation. Anytime you have a molecule that is positively charged, anytime you could reduce the charge on that particular carbon by either pumping electron into it, either by inductive effect or by resonance, that intermediate will be stable. So in essence, therefore, the more alkyl group that you have attached to the carbocation, the more stable the carbocation is. And that is basically due to an inductive effect because this carbon here will be pumping electron into the p orbital of the carbocation. Another explanation that we also give is that this here this here, if you look at this here, the hydrogen atom, of course, has an s orbital. That hydrogen atom is close enough to this p orbital to have, in essence, what we call an overlap, and that is what we now refer to as hyperconjugation. An overlap of the s orbital with the p orbital of the carbocation. That also minimizes the effect of the charge on this carbon here. So that also stabilizes the carbocation. So the point to be made here is the more alkyl group you have attached to the carbocation, the more stable it is. Or sometimes you could also use resonance to explain why a carbocation is stable. We are going to get to examples of those in the very near future. Okay, of course, I don't want to spend too much time on this one here. Okay, remember we gave you earlier, we showed you the reaction energy profile for the electrophilic addition reaction, in which we show you there is an intermediate carbocation that is formed. You see right here, this here is the transition state. Okay, the energy difference between the transition state and the starting material, that is what we call the energy of activation. Okay, so once you form the transition state, collapses to form the carbocation, and then that carbocation is also very reactive. It simply just go to a very small energy barrier to get to the final product. As you can see here, the final product has a lower energy than the starting material, and that is what drives the reaction. Okay, now I want to discuss carbocation rearrangement. Okay, so far everything has been straightforward. Now supposing we have this. Supposing we have that. And then we have this here, hydrogen bromide, reacting with this molecule here. Oh, this double bond is supposed to be here. We expect, what we normally expect to get is this right here. Now, supposing I tell you that is not the product. Supposing I tell you that is not the product. And this is the product. So based on what we told you so far, you will say this will be the product, right? The hydrogen is attached to here, and the bromine goes here. But what we find is that this is the product. This here is the product. Now, based on what we have told you about carbocation, you say, well, how could that be? Now, what we generally will tell you is to give the reaction mechanism for this. Now, what is actually going on here? In order to explain this, we're going to have to say that, of course, the carbocation is formed on this carbon here, right? That is the only way we can explain that. Okay, so what happens? This is what happens. The first thing that happens, Of course, just as we normally expect, the pi electron attracts the electrophilic proton, break the hydrogen-bromine bond, and then you form the intermediate carbocation. One thing we want to tell you about carbocation is they are very reactive. And anytime you form a carbocation, if there is a possibility for any kind of rearrangement to take place to form a more stable carbocation, it will happen. So what is going to happen in this case, you have a carbocation is formed right here, as expected. Of course, the bromide is here somewhere. And now, you're going to now have this hydrogen here will shift. Keep in mind what kind of carbocation do we have here? Secondary carbocation or primary or tertiary? Secondary, okay. Now this is now going to rearrange. This hydrogen will shift, what we call the hydride shift. So we have what we call the hydride shift. It will shift with the pair of electrons. Hydride shift to shift with the pair of electrons. Let me make some room here. Take this out. I'm going to write it up here. Okay, so what is going to happen? The hydride will shift. When it shifts, it breaks the hydrogen. The carbon hydrogen bond will break, and the pair of electrons will move with the hydrogen to now form a new bond. And so what we have, we now have to now form this carbocation here. Now we go from a secondary carbocation to a tertiary carbocation. Now, carbocation, I will tell you that they are very notorious. They will always form, the more stable carbocation will form either as a result of direct electrophilic addition or as a result of some kind of rearrangement. So now you form this tertiary carbocation. Now that tertiary carbocation now will now react with the bromide here, the bromide that we formed, we add here. To now form the product. So very often we will tell you to give the reaction mechanism for the formation of a particular product. You will get a lot of questions like that. Okay, now let us do one together. Yes. Okay, the way you know is, what we do, we will give you the starting material, we will give you this reagent here, then we'll give you the product. We say, provide a mechanism for this reaction. Yes. In other words, we will definitely give you the product. Very often, the product does not have to be the major product. We could simply say, just give us the mechanism for how this reaction took place. Okay? Yes. Well, what we call the hydride shift, the hydrogen with the pair of electrons will shift to this carbon here. Because by doing that, you are going to form a more stable carbocation. So the driving force for the process is the formation of this carbocation right here. Because it wants to form a more stable it wants to form a more stable species. That is just. Say that again. Okay. Okay, now let us do this. Supposing that we have this. Okay, can any one of you give me a mechanism for this reaction? Okay, let's go step by step. That are doing, right? Okay. So we have the okay, what happened first? The pi electron will attack the proton, right? Okay. And where will the hydrogen go? We'll go to this first carbon ray. All right, okay, good. Okay. Now what happens after that? We form the secondary carbocation, right? Okay. Okay, in this case, what we're going to have is what we call the alkyl shift instead of the hydride shift. Just a minute.
Why wouldn't it be chlorine? It's just so.
Oh.
Well,
Sorry. I have used so many bromine, I always think of bromine. Okay. Okay. So now we have, in this case, now we are going to get what we call the alkyl shift instead of the hydride shift. And what would that be? This methyl group will shift with the pair of electrons. To there, right? And then what do you get? From an intermediate carbocation. So what we are going from a secondary carbocation to a tertiary carbocation, right? And then what happens after that? The chlorine comes in as a nucleophile to attack the electrophile. The carbocation is an electrophile at this point. Okay? So it comes in, let's just draw a long arrow. Keep in mind, the arrow simply shows that you have a pair of electrons moving. Okay? And that gives you the final product. Okay, let's do one more before we leave this this particular topic. Yes. Yeah, you have to show all of the arrows. That is the what we're showing you here is the reaction mechanism. In the reaction mechanism, we're going to show us step by step how the reaction actually takes place. Okay. Yes.
So you're going to give us the first thing, and then we have to solve it.
Exactly. Okay. Okay, now let us do this. Supposing I give you this. Okay, I give you this starting material here. And I say, this is the product I was formed, or this product was formed. And I ask you to give the reaction mechanism, give the mechanism for this transformation. What would that look like? Of course, when you write a mechanism like this, we'll give you partial credit as you go along. Okay, we'll give you partial credit for every step that you show us. Yes. Okay, what will it look like? What is the first thing that happens? What is the first step? Okay, but electrophilic addition to the double bond, right? Electrophilic addition to the double bond. Okay, good. So, so reaction mechanism. Okay, so we have, let me just write this here. Okay, we say we have the attack of the double bond, right? Let's draw a long arrow. Okay, what will be the intermediate that will form? Okay, you do that. We'll give you point for that. Okay, so your intermediate here at this point. And the carbocation is right here, right? Is that right? It's on that carbon. Okay, good. Okay. Keep in mind we are going from a 5-member ring to a 6-member ring, so we need to be able to explain that using reaction mechanism. Okay, so what happens after that? The bromide is here somewhere. Okay, what happens after that? What happens? There has to be some kind of rearrangement, right? Alkyl shift. Did somebody say alkyl shift? Oh, okay. Which alkyl will shift? Which one will shift? This here or this here? Which one? Okay, that would be very good. That would be alkyl shift. So this carbon-carbon bond will break. It's just like any other alkyl shift. Okay. Form this. Okay, now this carbon right here is this carbon. Okay. Now this was the carbon here. This carbon right here. Remember this carbon right here. That was where this alkyl broke away. Okay, so what will happen to this carbon? It becomes a carbocation, right? So that becomes your carbocation, and this is positively charged. Okay, and at this point, the bromide now comes in. Attach this, and that's how you form this here. Okay, we could now write it in there because this is a 6-member ring. 1, carbon 1, 2, 3, 4, 5, and 6. Okay, and that's what we have. We have 1, carbon 1, 2, 3, 4, 5, and 6. Okay. So in other words, what we have here, the carbocation could always rearrange either as a result of hydride shift or alkyl shift to form another type or another carbocation, either a more stable carbocation. In this case, we are actually forming. We started with this carbocation here. That is a tertiary carbocation. We ended up with another tertiary carbocation. Okay. So these are the kind of things that you should expect when you come to carbocation reaction. Okay. Is that clear before we move on? Okay, then you guys should come and see me in the office tomorrow. Okay, let's see here. So now we have discussed carbocation rearrangement. That is something that we are going to be discussing in the future also. And the reaction we just did, that was this one here. That's what we just did. Okay? To get this product right here. Okay? Now, there is another type of addition reaction. So far, we have given you addition reaction in which we always been doing is adding hydrogen and bromine or hydrogen and chlorine across the carbon-carbon double bond. You could also add hydrogen and hydrogen across the carbon-carbon double bond. We call this hydrogenation. I could take a carbon-carbon double bond. Well, let me make it more obvious. Take this one out. Take this carbon-carbon double bond here, and then I use this reagent, hydrogen gas, in the presence of a catalyst, either palladium or nickel. We use palladium as a catalyst or nickel. So we call it catalytic hydrogenation. What? No. I'm leading to chapter 8 now. Okay. I will be getting to chapter 8 in a few minutes. Now we could add two hydrogen atoms across the carbon-carbon double bond. In this case, we get this product. We get the cis addition product. This is the kind of reaction we say it is a stereo-specific reaction. A stereo specific reaction. Now, what do we mean by stereo-specific reaction? That we only form one type of stereoisomer. Notice this hydrogenation here, anytime you perform hydrogenation on a carbon-carbon double bond, what are you doing? What are we doing? What are we doing? We're adding two hydrogen atoms across the carbon-carbon double bond. Folks, I want to tell you now, we are beginning to get into organic reactions. The best way to study organic reactions is to be able to say what the reaction is in your own words. Do not just write the reaction as an equation. You need to be able to say it. Okay, don't just look at this and say this is this molecule adding this reagent and you get it. No, you need to be able to say that this reagent here, hydrogenation, in which you use hydrogen gas in the presence of a catalyst will react with a carbon-carbon double bond such that you add 2 hydrogen atoms across the carbon-carbon double bond. Now the sp2 carbon that you started with now becomes an sp3 carbon. You need to be able to say that. That is the only way you're going to be able to understand all of this reaction. Now this is what we call a reagent. Okay? You need to be able to say that. Now, so in this particular reaction, hydrogenation therefore is what we call a cis. It gives us a syn addition product or cis addition product. I would say this is a stereo-specific reaction because we only get one type of stereoisomer. Notice we do not get the trans isomer. Okay? Now I bring this up at this point in order to also show you that we could use hydrogenation to establish the stability, relative stability of different types of alkenes. This is another example of hydrogenation. What do we have here? We take this trans 2-butene. We perform hydrogenation on it. We get butane. Keep in mind, all we are doing is adding 2 hydrogen atoms across the carbon-carbon double bond. So we get butane. Now, in the same token, we could take cis-2-butene, perform the same hydrogenation on it. We get the same product. Now, the difference here is the heat of reaction. In other words, the amount of heat that is generated in the course of this reaction, the heat of reaction or heat of hydrogenation in this case, for the transformation of trans 2-butene to butane is 116 kilojoules per mole. This negative sign simply tells you that this is an exothermic reaction. In other words, we are releasing energy. Okay, it doesn't mean that it's a negative number. No, it simply means that we are releasing energy. So in this particular reaction, using trans 2-butene, we generated this amount of energy. On the other hand, when we did the same reaction, forming the same product, with the cis-2-butene, we form this much, we release this much energy, 120 kilojoules per mole. Whereas, in the case of the trans, we release only 116 kilojoules per mole. What this is telling us is that the trans alkene is more stable than the cis alkene. These are the kind of experiments that we use to determine the relative stability of different types of alkenes. So this reaction is simply telling us that the trans alkene is more stable than the cis alkene because the amount of energy that is released depends on the amount of energy that was embedded in this double bond initially. So what that tells you that this double bond has less energy. When this molecule has less energy, we say it is more stable. Okay? Yes, go ahead. Yes, that's the point we want to make. Trans alkene is always more stable than the cis alkene. And therefore, we use this same type of experiment to determine the relative stability of different types of alkenes. And that leads us to the next slide. We have given you here the order of relative stability of different types of alkenes. Okay? Here, the most stable alkene, by the way, just as a background, if you look at this here, if I have this alkene, the carbon-carbon double bond in which you have only hydrogen attached to each one of those carbons. This is what we call non-substituted alkene. Non-substituted alkene, where you have each one of the carbon-carbon double bond is attached to hydrogens. There is non-substituted alkene. Now, if I now replace one of those hydrogens with an alkyl group, in this case, like this here, we now say this is mono-substituted alkene. If I replace with two alkyl group, we say it is di-substituted alkene. If I replace three of the hydrogens with three alkyl group, we say this is tri-substituted alkene. I bring this up because we are going to be using this. It is very, very important when it comes to the chemistry of alkenes. And of course, here we have the tetra-substituted alkene, in which all of the hydrogens have been replaced. Now, the point to be made here is, when it comes to the stability of alkenes, the tetra-substituted is most stable, followed by tri-substituted, followed by di-substituted, and followed by mono-substituted. As we also showed you in the last experiment, we also know that trans-alkene is more stable than the cis-alkene. This is very important going forward. So keep that in mind. Do not forget this. So at this point, I believe we have finished chapter 7. Now we are going to be going to chapter 8. What time do we have? You know, it's not 7:30. I got my own clock right here. We got plenty of time. Okay, so we got about 15 minutes to introduce you to chapter 8. Now keep in mind, chapter 8 is an extension of chapter 7. Some of what we've done in chapter 7 we are going to see also in chapter 8. Yes.
So for the section that one was by itself. You could also call that a non-substituted alkene, right?
Oh no.
Like let's say you were just looking at that one by itself, that one would be considered a non-substituted alkene. It all has methyl groups on it.
Oh no. The only non-substituted alkene is this here, in which you have both carbon-carbon double bonds are attached to hydrogen. Okay? Yes.
The example only applies to.
Yes. Okay. Okay, now let us get to chapter 8. Oni, can you go ahead and read for us? Just the first part of chapter 8, right here. Yes.
Addition of halogen, addition of hydrogen, addition of hypohalous acid, addition of water, acid catalyzed addition, oxide mercuration, demercuration, and hydrochloration.
Okay, thank you. As you can see here, just on this slide, there is a lot of reaction here. This is just the beginning of organic chemistry. Everything we've been doing so far is just preamble. Now we are starting organic chemistry, real organic chemistry. So this chapter, it does have a lot of reactions. So, but the good news is everything that you learned so far will help you in understanding everything we are going to do going forward. That is the good news. Okay. So in this chapter, we are going to, of course, start with the synthesis of alkenes. We start with the synthesis of alkene in chapter 8, and then followed by the different reactions of alkenes. As you know, we've already given you hydrogenation. We know that already, right? If I tell you to give me hydrogenation of alkene, you know what that is now, right? Hydrogenation is an addition reaction. We know that. Okay, so in addition to the addition reactions, of course, we're also going to do our oxidation reactions of alkenes. And if we have some time, we do our polymerization. By the way, most of the, the polyethylene, polypropylene bags that you use, okay, guess what those are? That is this molecule here. The polyethylene bag is this molecule here, joined together. Okay, that is and the way you make that is by polymerization. So hopefully we will get to polymerization before we finish this chapter. Okay, so now on the next slide, of course, you know what that is. That is the learning outcome objectives. So that means at the end of this chapter, you should be able to write structures for elimination reactions, products, write structure for the stereospecific products of addition reaction. You already know some of that. So anyway, so I will advise you to come back to this slide so as to refresh yourselves as to what you really do need to know relative to the chemistry of alkenes. Now, this slide simply gives you a variety of reactions that allows us to transform an alkene, a carbon-carbon double bond, to a variety of other products. By the time we finish this chapter, you will be able to do each one of these. In other words, you will be able to transform an alkene to an alkane that we know already. What kind of reaction would that be? That's hydrogenation. That much we know, okay? So you will be able to transform an alkene to a diol in which you add 2 hydroxides across the carbon-carbon double bond. You will be able to take an alkene and form a carbonyl compound. In other words, all of these transformations you should be able to do at the end of this chapter. So what this slide simply shows you is what I call the centrality of the carbon-carbon double bond in relation to synthesis of other organic compounds. So the carbon-carbon double bond is a very, very important functional group indeed. Now, let us start with the synthesis of alkenes. The first, for each class of compound that we are going to deal with for the rest of the semester, the first thing we do is to show how do we make these compounds. How do we synthesize these compounds? So let us start with synthesis of alkenes. So I will say acid catalyzed synthesis of alkenes from alcohols. Okay, if I have this very simple reaction, how many of you are doing organic lab? Okay, have you done synthesis of alkene yet? You done? Yes, okay. So some of you will probably do this in your lab. Okay, now if you take an alcohol, take an alcohol, this alcohol here, and you take what we call, you take water and acid. This would be what we call dilute acid, or you may want to look at the combination of the sulfuric acid and water as hydronium ion. You could do that. If you take that, this is what we get. Now this reaction is what we call dehydration. Okay, so this will be an acid catalyzed dehydration of alcohol. Acid catalyzed dehydration of alcohol. Oh, okay, very good. Anytime you have, very good question. Anytime you have sulfuric acid dissolved in water, it gives hydronium ion. So very often you simply see us just use hydronium ion. Or sometimes it could be hydrochloric acid and water, you get hydronium ion also. Okay, this is an acid-base reaction in which the water is acting as a base, picking up a proton from the sulfuric acid to form the hydronium ion, and then here, okay, the hydrogen sulfate as another species in the reaction product. Okay, so you form hydronium ion anytime you have any of the mineral acid, sulfuric acid, hydrochloric acid dissolved in water, you form hydronium ion. So many of these reactions you will see us simply just write hydronium ion. Okay. Okay, now. Huh? Yes, yes. Yeah, we call those, we are generally sulfuric acid, hydrochloric acid, could be phosphoric acid. Okay. Okay, so anytime you have them dissolved in water, you form hydronium ion. Now, this particular reaction here, we say this is dehydration, and this is an example of an elimination reaction. Remember, we told you earlier, we have 5 different types of reactions in organic chemistry. We're giving you examples of addition reactions. Now, this is an example of elimination reaction. Now, what is the mechanism of this reaction? Mechanism is going to be very big going forward. What is the mechanism of this reaction? In other words, how does this reaction take place? You got this already? Okay. Mechanism of acid catalyzed dehydration. Dehydration simply means you are losing the element of water of aqueous. So we start with I want to show all of the hydrogens so we know that these hydrogens were here before. Okay, so we start with the hydronium ion. So you start with your hydronium ion. Now it just so happens that the oxygen in the hydroxy group also contains non-bonding pair of electrons. That will now come in, acting as a base, picking up the proton, So this will be an acid-base reaction. And you form this intermediate. So we form what we call protonated alcohol. Now, this protonated alcohol is now set to lose water, because water is a very good living group. You are going to hear or say that it's quite a lot, living group. Water is a good living group. Because it is a stable species. And what happens? Lose water. And guess what happens once you lose water? What are you going to get? What do you think we get once we lose water? What? It's a carbocation, exactly. We are going to form a carbocation. Form a carbocation plus this water here. Okay. Okay, do not also forget, when we pulled off this proton here, we've also formed water right here. Okay. And of course, this hydrogen is here, and this hydrogen is here. Now, guess what now happens? This water now comes back again and now acts as a base, pulling this one of these hydrogen here as a proton, comes in, pulls that proton, and in so doing, the proton will leave behind a pair of electrons that will be used to form the pi bond. And the net effect is the formation of a carbon-carbon double bond and the loss of water. Notice that we lost the water here. Okay? So the net effect of dehydration is the elimination of water from alcohol to form a carbon-carbon double bond. Okay. Say it again. I said the net effect of this process here is the elimination of water from an alcohol to give a carbon-carbon double bond of an alkene. Okay? So that is what we're giving you here is the mechanism of the acid catalyzed dehydration of an alcohol. And of course, this goes to the formation of a carbocation. Of course, like all carbocations, this is also prone to rearrangement. Remember, carbocations will rearrange. So when we come back on Thursday, we will continue on chapter 8. Don't forget, let me give you back your, just a minute, let me give you back your